Diogo, you are muted.
Thank you, Rudolf. I was just trying to start things up. Welcome everyone to our webinar on PPDR. My name is Diogo Gomes. I'm a researcher at the Instituto de Telecomunicações, Aveiro, Portugal, and I'm the coordinator of Project 5GASP. This webinar is part of a series. We discussed the Project 5GASP last year. This year we're talking about the verticals. Yesterday we had a webinar about automotive, and today we have a webinar about PPDR. We will have today with us two sessions, one about network application that has been developed in the scope of the project, and we will have a guest speaker that will talk about chatbots in PPDR. I will introduce you further ahead our speakers, but for now, just to welcome you and to point you towards our previous resources. Our first speakers are part of the project, and they have collaborated in the scope of Project 5GASP to develop a PPDR application that follows NFVI architecture. I will give the voice to Kostis from the University of Patras, to Rudolf from ININ, and to Luca. They will forward the presentation in 3 steps. After that, we will have some time for some questions. We will get your questions through the chat, so you can either raise your hand or put questions through the Q&A button here in Zoom, and we will be gladly available to answer you. After this presentation, we will have a second session. So without further ado, Rudolf, go ahead.
Thank you, Diogo. Just a moment to share my screen. So hope you can see my screen. Can you confirm?
Yes.
Okay, thank you. So hello, good afternoon to everyone in this webinar. So let me first start with a short introduction to the 5G applications for the PPDR, which is one of the 2 vertical pillars within the 5GASP. So PPDR, as one may know, is about first responders and all about public protection and disaster relief. So in our case, and also for today's webinar, we have decided to present you something about how the 5G and the solutions we have developed during the 5GASP can provide us or can give us some help when we have to deal with the forest fires. So the forest fires are, first to say, a serious and increasing threat throughout the Europe. So it's partly due to the climate change and also due to the habits which are changing during the, let's say, last tens of years and so on. So so far as the most endangered states within the Europe has been identified, first Mediterranean countries like Greece, Spain, France, and Italy, and as well as Portugal is one of the most endangered state within the Europe. The forest fires does also have no mercy for other countries like Slovenia. Here we have last year in the second part of the July, the largest forest fire in the history of the Slovenia. So the right upper picture is from this this fire. So every forest fire, especially if it is a large one, is somehow endangers people, of course, the nature and wild animals, as well as the infrastructure. Therefore, our solution is is about the surveillance of endangered areas, And by this solution, we provide early detection, and in case the fire starts, this surveillance can give support for the first responders during the intervention. So let's now try to imagine a real world scenario. So it will be based, or it's based on the already mentioned largest forest fire in Slovenia, which took place previous year. So here we see the satellite image of this fire. It has affected more than 20 square kilometers. Well, it's a huge surface for Slovenia, but let's say comparing to large firefighters in other Mediterranean countries might not be so big one. However, our solution, or let's say our scenario, projects regular surveillance of the endangered area by the help of firefighter detection application, which is deployed or mounted, which used the drones. So for this task, we need a 5G network. So in order to stream the video, and we need to have a drone which will carry a camera, and then we need fire detection algorithms which run at some central premises where 5G core also runs. So this would be out of the surveilled area. So if we try to imagine the flow, the camera on the drone surveils the area, and then the video stream, or pictures are transmitted through the 5G network to the core site where the fire detection algorithms identify if there are any fires, or if there is any start of the fire. So in order to alarm the first responders. We can also imagine that if the fire will break out, then infrastructure, including some backhaul links, or so base stations, can collapse on, or can at least be damaged to the certain level where they're no more functioning. So in our scenario, we project that the backhaul link has collapsed. So now we can see on the map of this part of the Europe. So the red dot shows us the region where the fire has broken out. The blue dot shows us the central location where the fire detection algorithm has run before the fire has made the damage on the backhaul links. And then we have a green dot, which is where, with our solution, we can move these algorithms for the fire detection and surveillance support, to say so, can run further. So here in this solution, we use two network applications. The first one is isolated operations for public safety, which assure communication capabilities for the public safety users also during the disaster situation. So here we have, considering the 5G network, we have two operational scenarios. The first one is a day-to-day or regular scenario, where we have the base station on the field, and then we have a backhaul to transmit data and all the necessary stuff required for the 5G network to run to the 5G core network, which is located in the core site, somewhere in the central site. So as we said before, if there is a fire or some other emergency, a big emergency, the backhaul can fail, and then the central 5G core network will be no more available. So at that time, the isolated operations is activated, and the core network component is activated in the field on the cell site. So now we have a completely operating 5G network locally, and this will provide the basic services necessary for the public safety users. Of course, this site has limited capabilities, and therefore not all functions are available. The other network application is a fire detection and ground assistance using drones. So as said before, we have a drone on which the camera is mounted, and then it has also some processing capabilities, and of course the 5G modem, which ensures that the video stream is transmitted to the location where the fire detection applications works. So this would be for the introductions, and now we will go to the details with Kostis.
Yes, hello. Let me share my screen also. So that would be it, I guess. Please confirm that you may see the presentation view.
Yes.
Great. So this is an introduction, or rather a description of the first network application that will be involved during this demo, which is the drone detection application, namely FIDEGAD. So this is work done by University of Patras. And let me proceed to the next slide. So an introduction to FIDEGAD would be similar to what Rudolf said, to be honest. So our initial, let's say, approach, or our initial inspiration residing in the Mediterranean countries are, of course, the wildfires that are more than usual disaster and event happening every summer, and not only that. So our inspiration was exactly on this. And we foresee that in the immediate future, the disasters, or let's say the effect of the wildfires will be more massive. And apart from the threatening of the lives of the people, we can see many devastation of infrastructure, homes, and of course the natural forests. So what we have seen that as a measure to play a critical role of the restriction of the forest fires would be the timely detection. So what FIDEGAD proposes is to onboard an air drone with a cloud-native application, so as to reduce the spin-up time, and also have a server that processes the image and detects its fire residing on the edge, ensuring low latency. Telemetry from every possible sensor, for example, infrared sensor, speakers, conventional video, or thermal vision, can be transmitted through the 5G system to the teams on the ground and the first responders. So apart from the service creation time that can be tackled by containerization of the application, the service will also should also prioritize in switches between 5G stations if a backhaul failure happens. And this is something that we will see also during this demo. Right now, this application is near TRL6, so the technology can be demonstrated in a relevant environment. And coming to this, the relevant environment that we have in mind is the wider, let's say, metropolitan area of Patras. So we utilize devices and hardware in the University of Patras, like the drone and the processing servers, along with the Raspberry 4 that will be onboarded on drone so as to host the computational, let's say, needs of the streaming server. And the drone can operate in, let's say, in the forest area of Patras, which is near the city. So in terms of, in case of a fire, the timely detection would be crucial. And the drone should stream image through the backhaul link that is achieved from the center of the city through University of Patras to the computational servers there that can support the heavy duty detection image service that can detect fires. And from then the first responders or the critical services could access the streaming server or the streaming platform so as to have a first view or an initial assessment of the critical event. Moving to the high-level architecture of FIDAGAT, it comprises of two sides mainly, the FIDAGAT client and the FIDAGAT server. So the FIDAGAT client should be onboarded on an aerial drone and achieve connectivity through a 5G modem. And actually the image captured from the drone can be streamed to the image recognition service that can either reside on the Mac for low latency, or should be also delegated at the central 5G core, of course, with the respect that the latency will be increased. So the same service also hosts the control server, control center, which is, let's say, a UI for capturing the video stream, and also make some control actions like we'll see in the demo following. So getting a bit deeper to the architectural diagram of FIDAGAT, we see that the drone bears a Raspberry 4 Pi, and which is capable of hosting a mini Kubernetes installation that will be the host of the client-side application, which actually captures the video stream. And a WebSocket is active through 5G connectivity to the WebSocket server on the server side of FIDAGAT that accepts this video stream. So in the same service, image recognition service resides also that captures the stream and recognizes fire patterns. So these fire recognition images and alarms are pushed through a control panel through a web server and to the control panel browser that is accessible through a typical browser window. What you can see here is that we have bundled together the recognition service along with the web server that makes this browsing panel accessible. But this can be separated if we want better redundancy, or let's say to move the image recognition closer to the edge and the web server that serves the image to a centralized cloud. Now, the application components are, as described, are two. So the client service that resides on the drone provides the actual video stream. It has to be a privileged container so as to have access to the hardware of the host machine, which is the camera. And the input stream can be provided either from the camera feed directly, online streaming servers, if we want to accept stream from other drones, for example, or local files. Of course, local files are there for debugging purposes and does not have a crucial, let's say, implication in a real-life scenario. So what also the client is capable of is connected to multiple server instances of FIDAGAT. And this was quite crucial for redundancy. We may see it also in the demo that will follow, that a client tries to stream the capture image to the primary server. And if this connectivity with the primary server is abolished, then it switches the stream back to switches the stream to the secondary server and continues its seamless interaction with it and functionality. So if again the streaming, let's say the streaming flow with the secondary server is lost, then the primary server is being used again. And from the side of the FIDEGAD server, this service hosts the fire detection component that it consists of a deep neural network based on the ResNet 50 architecture, and currently it's trained out of Microsoft Coco dataset, common object dataset, filtering fire. So the integration needs of FIDEGAD are quite simple. It's based now on the NFV word, so it comprises of two NSDs, and the dependencies of the 5G system would be one slice. Of course, EMBP kind is the minimum requirement to operate. Also, the deployment of FIDEGAD is fully automated, as it's bundled as a VNF or a Helm chart, and it's also it will be shown during the demo that the deployment is on demand and not pre-deployed. So the first NSD, as you can see here, comprises of the client side of the application. As we expect that the latency would be minimal as it's placed on the UE, so there will be no latency between the UE itself and the client that will capture the video. It doesn't have to have internet access, of course, and the hardware requirements are kept on the minimum side, so as to host, let's say, mobile computer device as the Raspberry 4 Pi. The second artifact, which is the component of the service, which is the server side, also will be expected to have, let's say, a low latency, but it depends on it whether it is placed on Mac or on the core. But from what we have measured, I mean, in our scenario, typically both cases are below 50 ms. Again, the streaming, the server does not require internet access. And of course, the hardware requirements here are a bit more on the top of it because it needs to support the image recognition service. The delivery model is the same. So regarding the 5G readiness of the network application, so as to be considered a network application that interacts with the network, FIDEGAD right now supports both 5G interactions with the 5G system, as it is defined in the 3GPP specification, as you can see in this picture below, on the right below part of the screen. So it supports primarily the NEF interface through N33 interface, and it is programmed to accept, FIDEGAD is programmed to accept instantiation input during the deployment, which can be the NEF's location and authentication details that the NEF requires for application to interact with it. Also, it can subscribe to cell handover events, so it can detect when cell actually switch happened. Also, the second interaction, which will be focused on this demo, will be the PCF interaction through the N5 interface. And again, the FIDEGAD is ready to accept instantiation parameters like the PCF location, the SAPI, or the identity of the device that needs to be monitored, and the slice request information to the 5G system. Now this is a preview of FIDEGAD's UI. As you can see, it's a pretty straightforward UI that comprises of the video streaming and also the fire detection, if it is available. There is an option to disable or enable detection on demand. And as you can see in the right side of the screen, we have three basic, let's say, tables. So the first one is a table of fire detection alerts. So we can have some alerts when fire is detected. The second is interactions with NEF, and the third with PCF, respectively. Now, there is another button that will be utilized through this demo, which is the request priority button, and by pressing this button, the first responder can actually interact with the 5G system and request priority from this, and we shall see how it affects the user experience while interacting with FideGAT. A small, let's say, a minor preview of what we will see in the demo. The primary focus will be the AF or application function side of FideGAT and how it interacts with the 5G system. So from the 3GPP specification, we have seen that only trusted applications can interact with the 5G system using N5 interface or PCF interface, if we rather say that. And this is completely understandable because PCF will enforce a new policy through the 5G system, and such policy would be to have specific priority above other UEs, etc. So you do understand that an application that is capable of transforming the network or issuing such interactions to the network, towards the network, needs to be in the trusted domain. And so we foresee that this application is already trusted by the 5G provider. So in our demo, we shall see that the FideGAT client will stream video to the application server side of the FideGAT server that will capture the video and also make it available to the through the browser. And by requesting priority or by clicking the respective button, the application function of FideGAT will request priority towards the 5G system through the PCF interface. And this will happen through this specific interface and payload that, again, is fully described in the respective technical specification by 3GPP. So what we are seeing here is that the FideGAT will issue an NPCF policy authorization create command towards the PCF or the 5G system that already runs. And the implementation of it, actually, we can see a chunk of the implementation of it as the respective payload that will be sent is actually this one. It is defined again in 3GPP, and it comprises of a payload or a JSON payload that has an application ID, which is FideGAT, so it can know that this application is trusted. It has a specific DNN for this specific mission. Again, we have, so as to understand that this is a mission-critical application, this property that implies that the mission-critical video is being streamed needs to be present also. And the fourth property, which is the res prio, actually indicates that, which ranges from 0 to 16, indicates that an application that requests from prior 16 has the maximum priority over other UEs. Again, the slice information, I think it's quite self-explanatory. So the application would request a slice type of 1 and the slice differentiate of 0, so as to have the needed priority. And the final and the last property is the UE identification number, or SAPI, as we call it with the 5G system. So that would be regarding the presentation of FideGAT. If we don't have any questions, we can proceed with the presentations of the 5G system, that or the second network application, and then the video itself.
I think it's best that we have the video and then we go to questions.
So, Luca, the floor is yours.
Yes. Good afternoon also from my side. Let me just find the slides. Okay. Can you see it? Just a confirmation, please.
Yeah. Yes.
Yeah. Okay. So I'm going to start from Rudolph's slides. So basically, what we are doing with our isolated operations network application is we want to provide, let's say, a minimum disruption of the service for the PPDR users that are working on the field. So basically, this is the basic, let's say, goal or target with our network application. And as already was mentioned by Rudolf, we can, let's say, divide the operation into two modes. The first mode would be the normal operation, or let's call it day-to-day operation. So basically, in that environment, we can imagine G-node B or multiple G-node Bs that are distributed, let's say, across a geographical region. And then we have a central core to which those G-node B connect. And when we approach the, let's say, operation under disaster circumstances, when the disaster happens, as Rudolf has nicely described previously, we can imagine that some of the G-node Bs maybe will lose the connectivity towards the core that is their, let's say, primary core to which they are connected if everything is working normally. So in that case, what we can do is we can spawn or let's say activate a local 5G core on the G-node B itself. And in this way, we can provide those services, those basic services over the 5G network to all the users that are operating under the, let's say, coverage of this specific G-node B. So basically, this is the more high-level overview of our network application. So let's now dig into more details. So basically, if we wanted to achieve something like that, we needed to, let's say, somehow select components that we will use to provide this kind of services. So we did follow the NFV, let's say, model and try to use the cloud native approach to deploy our whole network application in that way. So basically, we have developed our internal images for those components that are involved in these network applications. Those components can be divided into, let's say, multiple groups depending on the goal that they want to achieve. So one of the, let's say, core components are basically the software components that provide the 5G system. So that means the G-node B component, the core network component, and also we have some components for, let's say, debugging and logging of those components. Then we incorporate also our own API and the UI, which will help us, let's say, managing this system with the network applications. And also, because we are doing isolated operation stuff, we involve the component that provides us the capability to, let's say, detect that the backhaul link was dropped and to activate the local core on the G-node B itself. So this whole network application was started, let's say, in the beginning of the project. We started to develop it as a virtual machine-based function, but it soon proved that maybe it is not the best solution for the goals that we want to achieve, mainly to provide, let's say, the minimum disruption to the users that are using our network application, and to be fast with deployment and stuff like that. So we finally packaged it as a CNF, that means container network function, and provide a Helm chart, which basically allows us to configure everything at the runtime of the network applications. So basically, we can with that we can basically achieve different operating modes. So we can instantiate our network application as a G-node B only, let's say, function, or the core network only function. We can deploy both functions in the same network applications, or we can deploy also alongside the IOPS component, which provides us the smart, let's say, detection and switch over to the local core. For, let's say, this whole scenario, we also developed some automated tests. So basically, we can test the operation of, let's say, other applications, or test the other applications, how they will behave when something like a disaster operations will happen. And this is something that we will also see in the demo that follows. So a little more details about the deployment itself. We are basically deploying everything as set as a Helm chart. So basically our Helm chart deploys the whole IOPS network application, which is in fact comprised of multiple deployment resources of Kubernetes. So you can see here that one component is, for example, a GNodeB, the other one is the core. As mentioned, we have some components that enables us advanced logging and debugging for the 5G system, our own API and UI, and also the component which will be responsible to provide isolated operations logic to our application. The services that are provided from the application itself are exposed in two ways. One, it's over the Kubernetes ingress, which basically provides the HTTPS-based service access of the application. And for, let's say, non-HTTP-based traffic, we provide a Kubernetes service provided with a host network of the node that hosts this application. Okay. So basically, how do you configure everything? Here I have the example of the Helm values, which are basically the input for the Helm chart when we deploy our network application. And as you can see in this example, we have some configuration parameters which can be configured at runtime of the application. So something regarding the GNodeB itself. So you can configure which band, which bandwidth, on which channel you will provide the radio network and stuff like that. On the right side, you can see the similar options also for the core component. So you can enable which will be the APN, which will be the slice that is provided and stuff like that, the network name, the IP addresses for the users and stuff like that. And also, because we are talking about isolated operations, we have isolated operations configuration options, which essentially tells the network application how to behave under the disaster situation. So essentially, we define the primary core IP. So this is the IP address to which the GNodeB is connected when everything is running normally. And as you can see here, we use ICMP, so that means ping, to check if this primary core is up. And after a pre-configured threshold, we can detect if the primary core at this IP is not reachable anymore. And when this happens, the GNodeB will reconfigure itself to connect to the core that is locally instantiated on the node itself. So you can see the IOPS core IP is the configuration option that tells the GNodeB how to reconfigure itself. So all of these values, this is just an excerpt of the whole, let's say, values template. It's much longer because we have many other options which you can configure. But when you, let's say, have everything configured as you would like, you can then deploy this natively over Kubernetes or use some orchestrator like OSM or do it through 5GASP portal to deploy the whole network application. So when we deploy this application, we usually deploy it over the OSM. And you can see here how it's let's say, the status when it is deployed is basically just running a Helm chart from the OSM. So basically it is expected to run smoothly. And after that, you can also see the whole deployment in Kubernetes, which as presented involves multiple deployment resources, which its deployment having its own pod, and also the config map, which you can see on the right side here, which includes those values that we set in the previously shown Helm chart. And at the end, those values that come from config maps are translated to the environment variables to the actual pod. So in that case, you can see that basically these are the variables that were sent to the GNode B at the runtime, so the GNode B can come up with the settings that we want. So now we have, let's say, an operational view of the system when it is up. So as previously said, we can run in two modes, that is connected to the, let's say, primary core or connected to the local core. So right now, in this example, we can see the UI of a system which is currently connected to the local core. So it's running in the IOPS mode, which is shown also in this bar, and the whole bar is red, so we can easily see that it is currently running, let's say, somehow in a disaster mode. And also, if we can check the settings of the GNode B, we can see that the AMF address on the GNode B, so that means the address of the core to which the GNode B will connect, is the local address. So it is connected to the core running in the same node as the GNode B. So here are basically the services that are deployed as shown previously as deployments in Kubernetes, and a lot of other data that is more, let's say, 5G oriented. On the right side, we can also see some users. So in this specific example, we can see that we have two active users, and also if we click on the specific user, we can see also some more, let's say, details about that user, about the radio ID, the IP address, which APN is using, and which slice it is currently assigned to. Okay. So when we deploy our network application, we deploy basically a working 5G system. So either way, if it is deployed in normal mode or if it is deployed in the let's say IOPS mode, it provides a 5G system. So if you want to, let's say, evaluate our network application, we also need something to connect to it. So for this, we are using, let's say, our own device, which we developed, let's say, not in this project, but in some other. But it is a 5G device capable of connecting to the 5G standalone network that we are establishing with our network application. And we can use it to, let's say, efficiently test our network application. Additionally, on this device, because it's, let's say, in-house made, everything from scratch, we can also provide a Kubernetes cluster on the client device. So that means that you can basically deploy third-party applications also on the UE device, which is connected to the 5G IOPS network application. And this is something that we will use in the demo that follows, because the client of the FIDEGAT will be basically instantiated on this device to, let's say, have a client that is basically behind the 5G radio network. Also to have some, let's say, to have some impressions of the performance that we are able to guarantee on this device. So basically, this device is currently working at 40 megabits, at 40 megahertz bandwidth in band 78 in standalone mode, of course, and we are using 2x2 MIMO. So basically, the performance that we can get from the network application, so from the 5G system itself, it's, let's say, in the range of 300 megabits per second in the downlink and about, let's say, 25 megabits in the uplink. But this also depends on the, let's say, setting that we select to deploy with. So basically, there are some predefined profiles which we can select from, and this way we can configure, let's say, to have more bandwidth in download or more bandwidth in upload and stuff like that. Also, we are capable of gathering some radio KPIs on the device itself, on the UE device. And here is the example of the new radio signal over the, let's say, 24 hours interval. And because it's a, let's say, laboratory environment, you can see that the signal strength are really stable. So this also means that the performance, as shown here, is pretty stable. Okay. So let's move to the let's say lessons learned part of presentation of the network application. As said at the beginning, we started with the development based on the virtual machines, but soon we were not satisfied with the deployment times and the complications with the, let's say, images or the Juju charms and stuff like that. So we dedicated some resources to basically do everything from scratch to provide the images. So we basically take the third-party software for the 5G system and deploy it as a container. And that was basically for us the most important thing to do, because this way we are really flexible on how we deploy, let's say, our application, G0B core network only, or all together with EOPS or not. So basically, that was the main advantage for us. Also, doing that, we can provide day 1, day 2 configuration scenarios for the orchestrator like OSM, because everything is included in Helm values. It can also be done from the OSM itself. So basically, we have a fully orchestrated network application. One of the advantages for us is also to use, let's say, the integrated mechanism in Kubernetes to provide us, let's say, self-restoration and high availability scenarios, because the Kubernetes itself includes some of those, let's say, required mechanisms to do that. As said in the previous part, the EOPS is based on everything that I just said, is for us just another service that can or not run on the G0B. And if it is a G0B with IOAPS deployed component, it can just reconfigure itself to use a local core. So basically, we can imagine at a certain geographical area, we have like hundreds of G0Bs connected to the core, and a part of them are also IOAPS enabled G0Bs. So in disaster scenarios, some of those G0Bs can just reconfigure it themselves to be locally independent 5G networks, providing the services to the PPDR users. So basically, for us, this is just a, let's say, add-on service on a G0B. And as hinted already by Kostis, we also provided an API for the third-party applications that can use it to reconfigure the 5G system that is deployed with our network applications. So, for example, application could request a higher priority and would send a request to our API, and in the back we will take this request and assign this application a higher priority by changing the slice in the 5G system. If we, let's say, finish with the lessons learned towards the PPDR vertical, we can say that we did the pilot implementation and validation of the IOPS PPDR concept in the 5G standalone network. This is something that was used in the LTE, but is not, let's say, used right now in the 5G network. PPDR applications can now use, and we verify that the API for, let's say, a slice reconfiguration for the important application. Other PPDR applications can also use our system to, let's say, test how they behave under the disaster operation, and when the G0B switches to the other core, how the application will behave and stuff like that. And also, as shown in previous slides, we have a 5G UE device, which can be also used to test the, let's say, performance of a PPDR slice that it's provided by the network application. Okay, so this is from me. So probably we move also now to the video, and then we go for the questions. Is that okay?
Yes, please. Let's launch the video.
Okay.
Nothing like a demo.
Okay. Yeah. Hopefully it will play nicely. So Kostis, probably you can start.
Yes. Yeah. Okay. So our initial setup, as shown here, is 3 domains in the Slovenia testbed. So it is the public node domain, the isolated operation domain, and the 5G gateway domain. So our initial, let's say, step would be that the core network is pre-deployed. It's fine. Look, it's pre-deployed in the core network. So what we do here is through the 5G platform, we order the initial setup for our, let's say, demo or demonstration of the application, which is the setup of the isolation operations node. So we will, this composite service that we see now being ordered comprises of the G-Node B that will connect to the core network, the public core network, a IOPS core network that will be idle in case of redundancy, and an idle FeedGate server that is ready to accept traffic. So this is the UI of our deploying platform. And as you can see, someone that orders it can see the deployment process of these respective services. We can see that the FeedGate server and the IOPS network is being deployed, and this is validated also through OSM's UI. As you can see, this is linked to a specific service order ID, which is the same as we can see in the UI. And as we wait for the services to be active, we can see and validate that the services come active to the OSM UI as well. So let's say the portal, the 5GAS portal, is an abstraction of the underlying infrastructure. As you can see, the first service is active, and the service order will be marked as completed, and you can see a graph of the comprised services. And as promised, we populate the IOPS node with G-Node B, an idle, let's say, redundant IOPS core network, and the FeedGate server that, again, is idle in the beginning, so as to accept, let's say, traffic after a public disaster happened. So this is yours, Luca. This is how 5G connectivity also is achieved through the IOPS G-Node B and the primary, let's say, initial public server.
Exactly. So we can see here now we can see here now the deployed system. So we will see 2 basically identical UIs, but we are seeing them in 2 separate nodes. So this node here is basically the G-Node B node, which will be capable of providing the IOPS operation. So basically, I will just do a play and pause. If we would check here, we would see that basically it is connected to the AMF. So this is the address of the core at this IP. So this is 10.5.154 something. So this is basically the running G-Node B. And now we will also switch to the core. So basically this is the core network. And as Kostis said, this is something that is for the sake of this demo, pre-deployed, because it emulates a core that is available at the telco provider's core. And we will also see that there is a user already connected to it. So this is this one here, and it is connected through the G-Node B. And this is basically the user that we saw that is connected right now to the 5G system. We could verify this IMSI that is highlighted here, that it is the same as the one that was shown in the previous part of the film. And this UE is right now connected to the 5G radio network and core of the let's say of the system. So I'm going to play some more. We can see some signal levels, and we can see that it's connected to the 5G and at our network. Okay, so Kostis, now you may proceed.
Thank you, Luca. So having deployed the first service, which is the redundant service that stays idle until the public disaster event, we can see how we can deploy the second bundle of services, which comprises of the primary FIDAGAD server, which resides in the public core network, and the client that will reside in the 5G gateway domain that will connect to the primary server and also to the secondary server that initially is idle in the IOPS node. As you can see, the services are being deployed in the same process that it was made in the first bundle. And of course, the primary server needs to be initially set up because the client needs, of course, the IP address or the location of the server that is only known after the server is being deployed. So the client, as we can see here, the client side of the application waits for the server to be active prior to being deployed. And as you can see, as we will see, the client is also active. And from the service characteristics, we can see, for the service characteristics of the client, we can see that it actually points to both servers. So the primary server is the one that starts with 10 point, which is the public, and the second is the local one, which is the redundant service, the redundant server. So again, as promised, the public node is being populated with the FIDAGAD server and the gateway node with the FIDAGAD client. And 5G connectivity is achieved through the deployed GNode P. So this is FIDAGAD's UI, and we can see it working on the public domain, as we can see with the IP on the top address bar. It's 10 point, means that it operates on the public network. And right now it recognizes as should fire. So again, this is the initial setup. And now I will describe how we emulate a public disaster event. And during this event, the public node will be abolished from the architecture, and the backhaul connectivity will be lost also. So this is emulated by a firewall rule that Luca will describe.
Yeah, basically, as you said, Kostis, we need to somehow emulate, let's say, a disaster scenario by tearing down the connectivity between the public core and the GNode B. In our, let's say, testbed, we can do this pretty easily by enabling a firewall rule, which will block all the traffic from the GNode B to the public core. And right now, we will see what will happen when this situation is detected by the GNode B, and after that, how the client of FIDAGAD will switch streaming to the service running on the IOPS node. So maybe I will just go back for a quick second. You can see here the logs of the, let's say, IOPS component running in the application. And as soon as it detected reachability problem, and according to our configured thresholds in the Helm chart, it will switch the operation to the IOPS mode. So right now it already detected in this phase there is a situation, and it's right now reconfiguring the GNode B itself. And here we can see that it is deployed with the new settings. And maybe I will just go back a bit, and we can see the major difference towards the first deployment. In AMF address settings. So right now you can see that the GNode B points to a local loopback address of this node, and that essentially means it will target a local core running on the same node. So after everything is let's say reconfigured, we also have to wait for the client to re-register itself to the 5G system. After that, it has the connectivity to the local core. And after that, we can, let's say, use the FIDAGAD server on the IOPS node, and client will start streaming to it because it cannot stream anymore towards the primary instance. So if I do play, we will see now the FIDAGAD instance running in the IOPS node by checking the IP address. Previously it was 10 point something, and now it's 172 point something, which means the local IOPS node. So basically, we can see that also the client switch itself nicely and uses the secondary node. So what we wanted to, let's say, showcase next is how we can use the ability to request higher priority for a third-party application like FeederGAT, which uses IOPS network application. So for this, first, we will try to saturate a network in the uplink direction, because this is something that this is the same direction as the video goes, so from the client to the core. So on the same UE device, which hosts also the FeederGAT client, we will run some iPerf in the uplink direction to try to saturate the uplink bandwidth. So this is something that you are seeing here. So right now we are sending iPerf, and we can see on the FeederGAT server instance that the FPS will start dropping because we are using the bandwidth with the iPerf. So this is the idea to see that it affects also the performance. And now we want to, let's say, use the ability to request priority from the FeederGAT application, actually from the FeederGAT server itself on this IOPS local node. And it will request a higher priority from the 5G system. So this will go to the API that was presented in my presentation previously. And in the, let's say, in the back end, we assign a different slice with the different capabilities to that same UE that is using FeederGAT, that is hosting FeederGAT client. So now we will showcase how we do a priority request. But firstly, we will check in the UI of the IOPS network application the current slice settings, so we can verify that it was actually reconfigured. So the first UE is basically the UE that hosts the FeederGAT client, and right now we can see that it uses slice 3 SST and SD10. So if we do play now and go to the FeederGAT server, we will request priority, which is triggered by this button here. And we essentially got the request back from the 5G system, okay, which means that the system itself has successfully applied the settings, and we can check then if those settings are actually applied at the UE side. And as we can see here, now the same UE is now the second one because this was re-registered. But we can see that the slice IDs are now different. So it's using SST1 and SD0 slice IDs. And the slice profile for this specific slice is to allow much more bandwidth to go through than on the previous slice. So basically, we should see now the FPS going back upwards also in the FeederGAT server application after this slice change was applied. And it went back to 10 plus FPS. So basically, I think that was it for the demo. Or have I forgot something, Kostis?
No, I think it was perfect. Let's leave our viewers, ask us if we forget something, something was bad.
Yeah. Okay.
Thank
okay,
you.
So that's from our side. Yeah.
Thank you, Luca, Kostis, and Rudolf for the initial presentation. So now we open up for a brief session of questions about this demonstration. You can use the Q&A, raise your hand. To jumpstart a little bit of discussion, I will do a question of my own. The TRL level of the IOPS demo that you made today, Luca, which is it now?
Well, I would say it's about 6 towards 7. Let's say it's something like that. You know, it's not production ready, but let's say it's a really good proof of concept also also, let's say, interworking with some other applications and using other technologies. So let's say it's pretty good tested, but it's in a production mode yet.
Questions? I will just leave one question for Kostis. The application that you showed up has a lot of potential to detect not only fire, but many other objects. Have you tried using different sources, for instance, satellite imagery? Any
Actually,
towards that idea?
yeah, actually, as you see in the presentation on the FIDECAD, I mean, the FIDECAD presentation, it can detect, or the training data set actually is quite broader than fires. So it just filter the fire output. Now, regarding the input, as you said, if the satellite, let's say, image is streamed through a public server, then it is accessible. Actually, we have seen it because in our integration, let's say, efforts during the project, through the project, we used a public, let's say, dummy, if I may say, video image that was actually online and streamed by Google. So it accepted the video stream, and it actually detected fire in this video stream as well. So to answer your question, if the satellite, let's say, feed is public and accessible through internet, then yes, the client can easily just accept this information in the instantiation parameters and have this as an input.
So my questions are mostly directed to possible use case owners. Okay, so PPDR institutions, people working in this area that might see the obvious use case for these tools. Clearly shown through the demo, showing that in the case of a disaster that everything can operate in an isolated way, but also showing the potential for future collaborations in this area. Thank you, Kostis and Luca and Rudolf again. We're a little bit behind schedule. So we will move to our next session. So we move now to a different type of use case. We will talk about AI-powered chatbots during emergencies. So in the previous demo session, we were focused on the work of first responders in the field, while in this session, the other side of the critical event management will be addressed. And this is the communication with the public. So during an emergency, traditional communications are slowed or disrupted due to heavy traffic, such as we showed right now. And therefore, a public warning chatbot could relieve some of the communication load by responding to questions about the emergency and thereby making timely information more accessible to the public. And although the chatbot is not yet available as a network application, we can imagine that it would be perfectly fit into the 5G ecosystem and may also benefit from 5GASP environments during development, testing, and validation. So without further ado, I would like to introduce you to our guest speaker, she's a chatbot expert. Her name is Jumana Al-Wafi. Hope I said correctly your name. She's a software engineer trainee at Everbridge in the Netherlands, and she studies software engineering at Saxion University of Applied Sciences and works on two projects, Common Alerting Protocol, namely on alert publishing website for the government of Spain, and an Everbridge public warning chatbot under the EU Horizon Engage project. Just to wrap up, Everbridge is a company that our speaker works at, and it is a software company that offers applications which provide information about critical events to help personal safety and business continuity. So, Jumana, please take the mic.
Yes. Can you hear me well?
Perfectly.
Yes. Okay. Thank you. So today I'll be talking about a CAP-enabled public warning chatbot. First off, for today's presentation, I will start off with a quick introduction. Then I will talk about what AI engines we're using in the chatbot, what advanced features we've been working on, a little bit about our demonstration session that happens in Norway this year, what's next for the chatbot in terms of functionality and performance, and then we can finish up with some questions. So first of all, I want to introduce the Engage program since the chatbot belongs under the Engage umbrella. So Engage is an EU-funded program that is aimed to fund research and innovation projects. It covers a wide range of topics from science and technology to social challenges and even industrial leadership. It also aims to foster collaboration between its different partners who are researchers, public organizations, and even private companies like ourselves. And parts of our participation to this consortium has been the development of this public warning chatbot. Okay, so in today's ever-changing world, hazards can come in very different forms, from natural disasters like hurricanes and earthquakes to public health emergencies like the coronavirus not so long ago. Events like this can happen so suddenly and unexpectedly that they leave us in fear and uncertainty. In times of crisis, the cost of making the wrong decision or even like not receiving reliable information in time can be measured not only by properties being damaged, but also in lives being lost. This is a stark reminder that amidst the chaos of a disaster, we often find ourselves at a crossroad, not sure of what to do or who to turn to for guidance. The significance of this issue became quite apparent in recent events where vital lines of communication, including news channels even, were disrupted or even overwhelmed. So today we delve into a critical solution, an AI-powered public warning chatbot that has emerged to address those challenges. It's been developed from lessons of the past, reshaping how we deal with emergency response, providing us with actionable information when we need it the most. So let's start off with what is a chatbot. So essentially, a chatbot is a piece of software where you can have an automated conversation with through text or text-to-speech. In order to get accurate and quality responses, we use artificial intelligence. So this is essentially what happens during an emergency. Vital lines of communication like news channels, authority systems, and even police lines face heavy traffic from citizens trying to understand more about the emergency. This traffic can potentially lead to those systems being disrupted or even blocked. So this is where the chatbot comes in. Citizens can now ask questions through the chatbot instead, reducing the load on those traditional communication channels and ensuring that accurate and quality, reliable information is accessible to everyone. So what goals do we have for the chatbot? Firstly, we want to quickly and efficiently deliver extensive information complementary to the initial public warning message. I will get into this point a bit later. Secondly, we want to ensure that critical information is accessible to everyone, especially those with language preferences. Since we are currently based in the Netherlands, we have the chatbot in both Dutch and English. However, we could easily implement more languages, depends on where our clients are based. And finally, I already touched on this point, which is reducing the traffic on the traditional communication channels by diverting the questions to go to the chatbot instead. So this is a bit of a background on how everything works. So we first publish an alert through the public warning platform, and we send a public warning message with a link to the chatbot to all the users. And at the same time, we send a CAP file, which is a alerts file, let's say, to the chatbot server. And once the users get the alert notification, it will have a link to the chatbot. Once they click on it, they get directed to the chatbot where they can interact and ask questions. The questions and responses will be handled with the help of AI models like Dialogflow and ChatGPT. So this is more of a visual representation of what I just said. So we have the emergency alert notification with a link to the chatbot, which is crisis.chat. If you click on it, you go to the landing page, the homepage of the chatbot, where it gives you information about the alert, how severe it is, description, when it starts or when it ends. And the red button is where you can click to ask a question, and it will redirect you to the chat page where you can interact directly with the chatbot and ask it hazard-specific questions. So about the AI engines that we use in the chatbot, we had an earlier version where we only use Google Dialogflow, which works based on intent and training phrases. However, we now have a second version where we use Google Dialogflow as well as ChatGPT, so a combination of two AI engines. So how this works is when you first ask a question, your question gets sent to Dialogflow. And if Dialogflow does not understand your question, or we didn't train it to understand your question gets diverted to ChatGPT instead. So instead of getting a response from the chatbot saying, sorry, I couldn't understand your question, can you try again? We send your question to ChatGPT, so you do get more of a suitable answer. As of currently, we have added what we call an AI driver. So it acts as an abstraction layer in which you can essentially switch out the current AI engines to any other AI engine, or even a combination of AI engines, and everything would still work correctly. So about the ChatGPT part. So again, if Dialogflow does not understand your question along with a CAP description is sent to ChatGPT as a prompt, and then the response is displayed to you in the front end. What does this prompt look like? It looks something like this. So let's say your question is, who is in charge, which is something we didn't train Dialogflow to answer. What we send is a CAP description from the CAP file, along with a static context, something like, as an emergency manager, can you answer? And then we put your question in and we send it to ChatGPT as a prompt, and then the answer would be displayed to you in the front end. So let's talk about improving instructions. So the chatbot was demonstrated in Romania early this year, or basically it was an earlier version of the chatbot where we had a demonstration session as well as a feedback session. And during the feedback session, participants got the chance to give us a lot of feedback on what they thought about the chatbot. And a lot of the feedback that we got was about how we deal with instructions, that no matter what question you ask about instructions, so what you should do, how can you prepare, what to do during or after the emergency, it would always give you the exact same response, which is what you see now, which is a big chunk of text about latest information in your area, what you should do now, what to do if you're a business. So it may not be relevant to a lot of people. So what we did is that we introduced a database. So now you can ask hazard-specific questions of how can you prepare, what you should do now, what to do once it's over, and it would have different responses. The responses are way more concise and straightforward. Not only that, we also now have images and infographics. So infographics about how to prepare for a landslide, for example. The picture in the middle, I know it's in Dutch, but it's basically what to do after the emergency. So who you should call based on the severity of the damage you incurred, and even an image about what you should have in your emergency kits. Not only that, but we also have video support. So we have instructional videos like the ones on the right, where it kind of instructs you how to act during a storm or how to act during a flood, or even videos like the one on the left, where it just explains the hazard itself or what possibly caused it. And the most recent feature we've been working on is location-based information. So you can now ask the chatbot how far you are from the emergency area, and it would first ask you for permission if you would like to allow or deny your location being accessed. If you allow us, then we will direct you to a different screen where we pinpoint your location with a marker, and we display at the bottom of the screen exactly how far you are from the emergency location in kilometers. However, if you happen to be within the proximity of the emergency location, then for now, we don't display a distance, of course. We just tell you that you are at the emergency location. However, we plan on developing this feature further, where we would want to display the closest shelter location or the closest safe area that you can go to in case that you are at the emergency area. So about our demonstration that happened in Trondheim, Norway, we demonstrated the chatbot at a landslide evacuation exercise. We had participants that got the chance to interact with the chatbot. And after that, we had a survey where participants could fill in to give us feedback about the effectiveness of the chatbots. In total, we got 33 survey responses and about 200 questions asked to the chatbot. This is one of the questions that we had. We asked, what information do you think a chatbot should provide in an active emergency? And as we can see, there's a spike for location, instructions, distance to emergency area, and multiple languages. And out of 4 of those highly recommended ones, we have been working on 3. So what's next for the chatbot functionality-wise? I do want to mention that Engage is finishing by the end of this year, but we do plan on developing the chatbot further. So we want to, as I already mentioned, the location-based feature to show the nearest location of a shelter or safe area. This could be even a police station, a hospital, or even a Red Cross center. We also plan on using the feedback that we got from a survey we did in Norway to develop certain features. So we want to focus on accessibility when we could add audio support for people who are disabled or are a bit old and cannot type. And we also plan on having more inclusivity. So when it comes to adding even more languages than we currently have. So what's next for the chatbot performance-wise? We are currently hosting the chatbot in a cloud system. However, the chatbot could benefit from an additional deployment on 5G multi-access edge computing with MEC. So we want to turn the chatbot from a user application into a partial network application by moving the chatbot closer to the mobile users. We aim to improve responsiveness and reliability when it comes to, for example, fetching instructions from the database or even displaying multimedia with low latency, or even when it comes to calculating the distance to the emergency location. However, we're unable to prove that and validate this approach since we don't have a MEC infrastructure. So this is where a 5G testbed could come in handy. Going even further, we're also wondering if we could run AI tooling similar to Dialogflow or ChatGPT on a MEC network. So yeah, this brings me to the end of my presentation. Please feel free to try out the chatbot at crisis.chat or by scanning the QR code. So yeah, I'm open to any questions.
Thank you, Jumana, for your very interesting presentation. We already have some questions, so we can jump right into them. So Chris is asking, do you have a distribution workflow for the chatbot?
A distribution, so the chatbot is currently still a prototype. So it's just it's a blueprint. So we don't really have a distribution workflow.
I think that here the question is more about how you let's say organize the information in the chatbot so that you can provide because you need to give information for the chatbot to release to the public. So how do you manage that information? Do you leave it as a text that the chatbot indexes and you just question it like ChatGPT? Or do you have a plan like you usually have in IVR? So when you call it a call center and you have to go through these trees of questions and answers, how does it work?
So do you mean with how information gets to the chatbot? So the information that we display all comes from authority. So we use CAP, which is what I mentioned. So once an alert is published, which comes from the authorities, this is sent to the chatbot with the diagram that I displayed. So when the messages go to the public, at the same time, we send the CAP file to the chatbot. So it's all reliable information that comes from the authorities. And that is what we use to answer the questions. Does that answer the question, I hope?
I hope, yes, Chris, you can reply back. Chris also asks about the feedback mechanism apart from fallback to ChatGPT. And this is one of my questions, which is, so if you're answering based on those CAP files, which have information about the event, how does ChatGPT know more stuff? Because that's something just released. So how does it get?
So again, so when Dialogflow doesn't understand the question, that's when we divert it to a ChatGPT. But how does ChatGPT know? Because in that prompt, we sent part of what we have in the CAP file. So we sent a whole tag that has a description about the emergency, where it is, like the slide that I showed. So it shows a lot of information about the location, where it is, how far it is, how big it is. All of this information is sent to ChatGPT along with your question. So that's how it comes up with the answer.
Okay, thank you. That helped me. But more questions? People need to type in because this is a webinar. So I will put in an extra question. So I saw that you wanted to try this using an MEC, multi-access edge computing infrastructure. What advantages do you see from MEC? Because chatbot it does not rely on very low latency aspect because we're texting, right? And even a voice application, I don't think it's important. So I would say that you're worried about the information that you can collect from the edge. What is your insight? What things do you see as promising from MEC?
So what we were thinking was having the MEC infrastructure where the location is, the location of the emergency, to have lower latency when it comes to displaying multimedia, because even right now when we're testing it, it seems to have that loading indicator even when displaying information from the database or images or even videos. Videos take a lot longer. So we were thinking we would have the MEC at the location of the emergency. However, people who are not in the emergency location would be handled with the chatbot hosted on the cloud system, which is the version we now have. So I was thinking that MEC is a lot more reliable and faster when it comes to displaying multimedia, and when it comes to, again, having a lot of traffic at the same time, it could take longer to display.
I understand you. So your point is actually using multimedia, and that would of course require some low latency services. So Chris just confirmed that he got his answer back. More questions? There are no more questions. I would like to thank Jumana for her time. A very interesting talk about chatbots. I think that's a very interesting network application. For sure that networks can benefit from these types of applications, and especially in PPDR use cases, because this is usually PPDR situations stress a lot the network, and this can certainly offload much of the stress from first responders and put AI to work.
Yeah, thank you for your time.
Thank you so much, Jumana. I would like to thank all the speakers today. I also like to thank the audience. We are closing this series of webinars. We will have a final webinar. It will be next year on the closure of the project, where we'll present our final results. Hope that this has been insightful and that we have provided you with useful information for your work and your projects.